So, we will work out some examples. Now, this is slightly more complicated. So, everybody is clear about this. So, you can compute given the velocity. So, you see Fourier space is useful, you agree that it gives you some more handle. In fact, you can visualize it if you just get used to it and see what they mean. Now, this example has velocity field like this. It is 2D field, it is only function of x and y, and they are in the plane. Now, A, B, C will interact. So, what are the Fourier modes in this? So, this is 1 0, this is 0 1, and this one is sin x plus y. So, e to the power I x plus y minus I x plus y by 2 and 2 I. So, this is 1 1 and minus 1 minus 1. So, what happens? So, 1 0 1 1 0 and 1 1. So, if I add these two, I will get 1 1, right. So, they will interact non-linearly. So, k equal to p plus q. So, this is q, this is p, and this is k. So, we will see nonlinear interaction for this example. Now, because of nonlinear interactions, the b, c, and a, these are amplitudes, will change with time. So, some energy will go from A to B, or something could happen, right. Non-linearly means it will start doing exchange. Now, the question is how to get this evolution. So, now this is a real question. Now, we need to find d by dt of u of k. Now, u of k, so you see for 1 0 1, my u of k is b. So, this will give you basically I am looking for b dot. How does b change with time? So, that's the objective, and the some of the midterm project I am going to give you is like this, more complicated. Okay. So, this example, please see this carefully, and we will try to understand. So, my modes are 1 0 1 0 coming from here, and minus 1 0, and amplitude is c. It has only y component, this y hat. So, y hat here, okay, ui. This one is 0 1, right, cos y is 0 1, ky, and it has only amplitude along x direction, x hat. So, this bb. This one is 1 1 and minus 1 minus 1. It has component along x and y both, and the amplitudes are just minus, these are the 4 amplitudes. Okay. So, if I draw this picture in Fourier space, the 3 Fourier modes are, well, there in fact there are more of them. Okay. So, they are like this, no, they are not here, sorry. There is a complex conjugate always exists, right, to the reality condition, it better exists, this exists, this exists, this exists. Well, sorry, basically this is same as this, it is a triad. K equal to p plus q is satisfied here, and they are interacting nonlinearly. Okay. Now, so I would like to compute the nonlinear terms first. So, our idea is to compute d u k by dt is, what is that? So, I put n k in the left, now that is my notation. So, this is a plus n k n u k equal to minus grad p minus I k vector p k. Viscosity we will ignore right now, I will not put viscosity for this. So, these are the terms which we got, if you recall this. Okay. Plus viscous term plus force. For force I will say there is no force and there is no viscosity. So, energy will be conserved among this interaction, and we should get all that. So, let us compute the nonlinear interaction. So, our idea is to compute d u k by dt is, what is that? So, I put n k in the left, now that is my notation. So, this is a plus n k n u k equal to minus grad p minus I k vector p k. Viscosity we will ignore right now, I will not put viscosity for this. So, these are the terms which we got, if you recall this. Okay. Plus viscous term plus force. For force I will say there is no force and there is no viscosity. So, energy will be conserved among this interaction, we should get all that. So, let us compute So, I am going to denote this is P and this is Q and this is K. So, P is 1 1, K is 1 1. So, this K 0 1. So, by the way this porting, so this 0 1 is same as here. So, 0 1 is P and this is Q. So, you denote like that. So, nonlinear term is a convolution. Now, convolution real computation is being done. Please focus on it. So, I will share this slide. So, do not take all the steps, do not write all the steps. So, convolution is k dot u q u p sum. So, you have to sum over all possible p's. So, once it will come as u p and other time it will come as u q. So, first k dot this k with u of p u of q, this one k with u of q, then u of p. So, this one, then take k dot u p, then multiply by u of q. So, this is a vector. So, this is a scalar quantity and there is a u of p. Okay. So, this is what convolution means. So, we can do this step by step, all of it. Now, I will not do this step. Okay. So, let me just do one of them. K is 1 comma 1, right, dot u q is here 0 comma c. What will it give you? Just c. Okay. And u of p will be b y hat, b x hat. So, this is a vector which has amplitude c b x hat dot product. No, C B, are you happy with this? C B x hat, this is what we will get. Same thing, well, you will get something similar for the next term. So, if I do all that, now this is that. So, first one I computed B C x hat, second one is B C y hat. Okay. Now, all these are labor and some of it we need it for our research, we need to do all this stuff, but there are simpler ways to do it which you will learn later. But first thing is you should just do them methodically. Now, you can apply the same logic for other Fourier mode. So, this will be, now this step I am not showing you, but you can do it. In fact, I want you to do it. So, this example is there in the notes, you should look at it, and in fact, you should do it yourself and verify, and you can do with NUP. Now, given nonlinear, so what about pressure term? So, you know how to compute pressure term. So, minus k squared p is I k dot n k, something like that, no? I may not get the sign right, but this is what it is. So, I can compute pressure. Since I know the nonlinear term, now I can compute pressure. No n hat, just n it. So, do the algebra, then you get, so this is a formula, okay. And these are 3 pressures, they are all non-zero. Now, once I know the pressure in nonlinear term, now I can get d by dt. Okay. So, d by dt of, it turns out uk has 0, d by dt of uk is 0. Now, this by plugging in, you just plug it in, you will find it 0. duq is non-zero, it is that, and dup is this. So, I get non-zero values here, but uk is 0. Now, how do I get a dot, b dot, c dot? So, uk, now if you look at your notes, uk is a by I x hat minus y hat. You can see the, so this is what, so I had this u of k like that, no. So, it is x hat minus y hat, but d by dt of this, so x hat and y hat are constants. So, if I take d by dt of this, then it will act only on a. So, that implies a dot is 0. So, a does not change with time. uq, so q is 1 0. I probably have this in the next slide, but let us do it here. uq and UQ10 has y component C. So, it has y component, it is amplitude is C. So, this is the d by dt of C y hat, that is left hand side because UQ is C y hat. If I take d by dt, what will I get? C dot y hat. So, C dot is AB y hat. So, C dot is in fact AB y hat. This implies C dot is AB. So, you are writing in a vector form and then picking up the components, and this is a simple example, and you can get all this stuff. And similarly, from here I get B dot, UP has B in it. So, that gives you B dot is minus AC. So, these are how we derive equations for the evolution of these amplitudes. Now, this is easy solution, no? These equations are easy because A dot is 0, that means A is constant, and so this equation is like oscillator equation for phase space. So, this is easy solution. B dot is minus C and C dot is B. So, it is oscillation, and solutions are this. So, they oscillate with frequency A. Okay. So, they mean something. So, this means my modes are blinking in time. So, if you see a pattern which will be time dependent and they will be changing periodically in time. Okay. But we will understand it bit later. So, we will try to interpret them when you do convection, hopefully we get enough time. So, these are how we see these patterns in nonlinear physics or in flows. So, any questions on this? So, just to tell you that we had a flow where the nonlinear the modes were interacting with each other. There is interaction, the amplitude of the modes could change with time, and we derived equation for those amplitudes, and from that we can also solve it. This was easy to solve. Okay, now this is this equation. Now I am going to come to, well, so there is one more nice trick. So, before I go to the next example, which I want to just say this. So, let us look at this A of k, U of k. So, there is a algebra can be reduced. Okay, there is a nice trick which decreases the complexity by half. So, this is my k vector 1 1. Now, this is my equation, right. So, I took nu to the right hand side, I get this. Now, I know my velocity vector is in that direction. So, I can take some kind of direction. So, this is, I really did not write as unit vector, but this is a direction vector along u of k. So, you take a dot product of this equation with a direction vector. I would ideally like unit vector. Let us make this unit vector. Okay. Unit vector is x hat minus y hat by 2 by square root 2, that is unit vector, no. So, I dot product this equation with unit vector. So, what happens to the pressure term, this term? It becomes 0 because this is along, the pressure gradient is along this direction. So, this term disappears, and the first term is very nice. In fact, that will be proportional to A. You put the unit vector, then amplitude of the unit vector in 2D will come as only one number. So, this becomes like A dot, and you get E. I need to do this unit vector k dot. In fact, I have in the next slide, next equation here. Okay, nu dot x this thing. Now, I have computed nu before, and that was x hat plus y hat. So, that is x hat plus y hat. Okay. So, this is x hat plus y hat. We did compute before. You need to compute this. Okay. Now, we will simplify that calculation further by some nice tricks, but dot product of this is 0. So, by choice of your basis function we can eliminate pressure term, and in fact this is called Crea-Haring basis. Is in fact it is not fully, we will do more discussion, but that is for the tomorrow's class. So, we are going to make some basis functions which will simplify our calculation, and I need this, at least for my work we need this stuff, and you should also be able to do it when you do your project or you do homework. So, I want you to basically understand and do them for simple problems. We will do another example. So, in fact we can just do it. So, by this idea, so just use the unit vector along the direction of the velocity field. Okay. We will do this in more detail, but I just want to motivate that we can get rid of the pressure term by appropriate choice of basis. Okay. Now, this example is more complicated, so I will not going to do all the detailed calculation, is there in the notes. So, my velocity field has again 3 unknowns A, B, C, but they do look there are more terms, no, I mean this is like this one has long terms. So, the first one is 1 1, right, sin x cos g. So, we do not want to get into big detail, but it is 1 1 1 minus 1 combination of 4 of them. So, but y ky is 0, but kz is not. So, here kz non-zero, kx non-zero. So, this is 1 0 1, this one, and its amplitudes are u of k. Well, I have more of them, minus 1 0 minus 1 and so on, but I am looking at only one number, one Fourier mode, which is 1 0 1. So, this is this one. What about this yz? So, ky kz, this is 0 1 1. So, this is this one b, no. So, b sitting here. What is this? Sin x cos y cos 2g. So, 1 1 2. So, this is 1 1 2, and its amplitudes are is a 3D, it is computed along x, computed along y, computed along z. So, this is, you can compute them, it is like this. Now, this is bit of work, but once you have u of k, you can also compute omega k and so on. It is, you can compute the helicity, it is 0. Okay. So, there are many 3D fields which are non-helical. So, this. Now, how do we compute A dot, B dot, C dot? Now, it's more complicated, but it can be done. Now, I just want to tell you is a physical example. This is an example of 3D convection velocity field. So, this will be a roll along yz plane. X is not changing, no, so it is a yz plane. So, there is a, you can think, so this axis is like that direction, it is like going like this. The mid one is xz plane, no? So, it is going like this or going like that. So, it depends on the sign of the amplitude. So, imagine the rolls are going in that direction and rolls are going in that direction. If there are only two modes 1 0 1 and 0 1 1, they will not interact non-linearly. They are happily independently doing their rotation. But as soon as you put this mode 1 1 2, then there is a interaction. So, then there is a person who will make them talk, and they could exchange energy among them. So, this third party is going to make them work or make them talk or make them exchange energy. And so, without 1 1 2 there is no talk, but with 1 1 2 there is a talk, and we can work out the nonlinear interaction. So, this one I want you to look at the example and you do it yourself. So, my 1 1 2 mode is here. So, this is a, so I am not drawing the vectors, huh? These are, in fact, if you want, these are 1 1 2 is here. So, this is a different way to represent them. 1 1 2 right now is a node, this is 1 1 2. So, each of these dots represent a lattice, a wave number lattice. So, in fact, this is, they represent the coordinate. This is a tree diagram. So, this is not really coordinate, but this is a schematic of how they are coupled. So, 1 1 2 is coupled with these two modes. So, I put minus sign y because this is by intention. So, is a in fact more correct way to do it. So, sum of, so we call it this one. Okay. So, if I look, you add them 3 vectors, then I get 0. So, I call it, I choose a notation k prime equal to minus k. Okay. So, we need to do all this stuff because when calculation is large, we need to do all this technology. So, you see that all of them triangles, if you add the kx component, it becomes 0, ky component 0, kz component, you sum them up 0. Same thing here. Now, 1 1 2 has only one channel. So, this triangle, right. So, 1 1 2 is, so this is k p q, or I could have written, I could take this to the left hand side. So, I will get k plus p plus q 0, then this becomes minus 1 minus 1 minus 1 minus 1, right. But if I want to write k equal to p plus q, then there is a channel, is this is the only interaction, there is no other interaction possible. But 101, which is here, can get energy from 112 by this channel 112. So, there is a channel like this for 101, but it also has another channel here. So, 101 is affected by 2 channels. So, one channel is here, other channel is here, they are independent channels, but they are 2 different channels. I will not say independent channels, they are 2 different channels, and I need to add contribution from both the channels, then only I get correct answer. I will, otherwise I will not get correct answer. Is that clear? So, when you write sum, no, so you write sum p u k dot p k dot u q u p, then I need to sum over all p's. If I leave out, then I will not get correct answer. So, this mode couples via this triangle as well as this triangle. We need triangles. So, this is an example which I think somebody asked. We have many channels, and you need to account for all the channels, and which one contributes more, which can more, only after you do these calculations you will know. So, 0 1 1 also has 2 channels, one is this channel, other one is this channel. So, I urge you to do this calculation. It is done already, but you have to do this, see how it is done. So, nonlinear term will be like this, pressure is like this, and the time derivative of these are like that. Now, if I turn off the viscous term, then you can get, if you turn off the viscous term, I get these equations which are not so straightforward, and so this is without viscosity. So, these are the 3 nonlinear equations. Now, A dot is not 0 for 3D. So, we got A, B, C, all of them are changing in time. So, one interesting point, which in fact this is a physical example, okay, this happens in convection. So, B is oscillating around a mean value. See, these are amplitudes. So, B is green, B, but it is oscillating because all of them are interacting. Earlier A was not changing, but here, so B is oscillating around one mean value, and A and C are oscillating around 0. So, C is the black curve which is oscillating around 0, this 0 line, and A is oscillating also around 0. So, B is fixed, but A and C are oscillating around 0. So, this happens in convection. So, we have a roll, let us say in that direction, and we have a roll in that direction. Okay. So, it is a 3D roll structure is, in fact, if there was only single roll, then it is 2D, is going in a plane, and there is no variation along that direction, but the roll in that direction, there is a roll in that direction, and I couple them by this 1 1 2 mode. So, one roll is strong. So, there is one big party which is very strong party, and the other party is weak party. So, weak party comes and goes. So, in fact, it can disappear, the weak party. So, I will show you maybe a picture next time. So, we see this blinking of this weak mode which appears and disappears, but the nonlinear this big roll also blinks, but around a mean value. So, this roll is very strong, but it also blinks, but then the weak one continues, well, weak one appears and disappears, and the person who is also helping, you know. So, this B is a big this is a strong roll, and now we can so this is a helper, C is a weak roll. Okay. So, the structure was like that, no? C was along xz plane. What was it? So, we had this, one was xz plane, other one is C was xz plane and B was yz plane. So, this is yz plane, this is xz plane, and this is 3D, and that is helping, that also oscillates. Helper also is not kind of, it does not, his bank balance is also going up and down, you know, in this interaction. So, that is how they interact, and this is all by nonlinear interactions. Now, this is I have not discussed yet, but this is how much energy gets exchanged, so that we will do later. Okay. This to be done later. So, you need to, in the today's lecture, we need to worry about only these three. Okay. So, we will stop. Thank you.